when you're working with
Now, as soon
probability.
as we have an event E in mind, we can begin to talk about its complement. The complement of an event means simply the opposite of the event. If E is an event, its complement is signified by E with a superscript C, and it's always true that the probability of E plus the probability of its complement adds up to 1. And therefore, if we were to subtract this term from both sides, we'd get this very handy rule: the probability of E is equal to 1 minus the probability of its complement. Let's look at an example and we'll see how we could use this rule. With a coin toss, if we assume the coin is fair, then the probability of getting a head on a single toss is 1/2, or 0.5. Our experiment is going to be this: we're going to flip the coin 2 times in succession and ask what is the probability that we will get at least one head. At least one head in 2 flips is our event E. What we want to do first of all is to list all of the possible outcomes of running this experiment. Well, here they are. You could get 2 heads, you could get 1 head on either the first or the second toss, or you could get no heads at all. In other words, get 2 tails. The first option for computing the probability of E, that we will get at least one head, is to simply list all of the possibilities. That we've done. When you list all of the possible outcomes of running an experiment, you've listed what is known as the sample space of the experiment. It's simply all of the outcomes that could occur. If every outcome in the sample space is as likely to occur as any others, then we say that the sample space is equally likely. And this sample space is equally likely. A pair of heads, say, is just as likely as a pair of tails, and that's just as likely as getting a tail first, followed by a head. In an equally likely sample space, the probability of an event A is simply the number of ways to get the event A in the sample space, divided by the number of things that's in the sample space, or the number of all possible outcomes in the sample space. So in this particular case, E is the event that we get at least one head. We look through our sample space. There are 1, 2, 3 ways of getting that. Divide by the 4 that are in the sample space, the probability of E is 3/4. If E is the event that we get at least one head, then E complement is that we get no heads. The probability of the complement, well, there's only 1 out of these 4 that give the complement, and therefore the probability of the complement is 1/4. Notice 3/4 plus 1/4 does add to 1, and that's just what we were claiming when we began. If you add the probability of an event and the probability of its complement, you should always get 1. For the second option then, for computing the probability of E, we can always get at it by means of its complement. The event is at least one head. Its complement is no heads at all. The probability of the complement is 1/4, since there is only one of the 4 equally likely outcomes that give this event. 1 minus 1/4 is 3/4. That is the probability of E, and it does agree with what we got just by counting. We'll see the value of the complement rule if we make this problem a little bit more challenging. Suppose now we wanted to toss the coin 10 times. What is the probability that we'll get at least one tail? Well, first of all, we need to think of how many possible outcomes there are. Remember last time when we tossed the coin twice, we found that there were 4 outcomes. The reason is that the first time you toss the coin, there's 2 possibilities, a head and a tail. And the second time, there's 2 possibilities, a head and a tail, and 2 times 2 is 4. If we were to toss the coin 10 times, we'd find that we'd simply have a string of multiplying 10 factors of 2 together, and that would give us a total of 1,024 possibilities. how many of those have no tails? Well, there's only one. Namely, it's the outcome that's composed exclusively of heads. So if the event E is at least one tail, the complement is no tails, the probability of the complement is 1 out of 1024, and we would subtract that number from 1 in order to get the probability of E itself. And we get that probability then quite easily simply by computing the probability of the complement and subtracting from 1. Let's move on to a different kind of physical situation. We would like to be able to get more than two possibilities coming up each time. So let's say we're going to now roll a die, a fair die, and record the number of dots that are showing on the top face. Of course, the sample space for this experiment is 1 through 6. And if the die is fair, the probability of each of these outcomes is the same, so 1/6 for each one of those. And we could make a probability distribution here if we'd like to. And we have another equally likely sample space. The purpose of doing this is not that it's so interesting in itself, but to transition then to one that's a little more